Salam. Welcome everyone. In this session, we have the presentation of Meysam Madadi from the University Autónoma de Barcelona. This is a short biography of Meysam. Meysam Madadi obtained his MS degree and PhD in computer vision at the University Autónoma de Barcelona in 2013 and 2017. He is currently a postdoc researcher at Computer Vision Center at the same university. He has been a member of Human Pose Recovery and Behavior Analysis Group since 2012. His main interest is human pose estimation and garment modeling. All right. In this session, he will talk about deep learning advances on human pose and shape estimation. The talk is a recorded video. After the talk, we will have some Q&A. Please ask your questions in the comment section. Let's play the video.
Hello, this is Meysam Madadi. Welcome to this talk. In this talk, I will consider deep learning advances on human pose and shape estimation. First, let's define what the human pose is. A common definition is the location of human skeleton joints, either in 2D coordinates in pixels or in 3D coordinates in millimeters. This is the simplest definition, and it does not show any structure among the joints. Body bones can be used to connect relevant joints in a kinematic tree defining a structure. One problem is that human body has more than 300 joints. All these joints do not represent the same importance, and annotating them is a challenging task. Therefore, in the literature, it has been shown that a set of 14 to 20 main joints are enough to represent the pose. However, this is a minimal representation of the body pose. Other richer representation can be also defined to deal with body shape as well, like cardboard models or parametric models, like these ones. Okay, but why do we need to study human pose estimation? Human pose estimation is one of the most important problems in the computer vision field. In this chart, I show you the most used keywords in the last 3 years on CVPR. I highlighted some keywords relevant to the human pose estimation. For instance, 3D human shape estimation. As you can see, all of them appear among the top ones. Each year, hundreds of papers are published on this topic. Pose estimation is an important problem from an application point of view as well. Humans are part of many daily life photos or commercial imaging. Pose estimation has a broad application, for instance, in movies, virtual reality games, human-computer interaction, animation, sport analysis, and etc. Human pose has many degrees of freedom, and manifold of valid poses is quite nonlinear. This makes pose regression challenging. Along with this, there are many other challenges in the pose estimation, such as viewpoint, rare poses, closing, occlusions, illumination, cluttered background, and even unrealistic images like these ones. Okay, human pose estimation has a broad list of domains and techniques. I classified pose estimation into 4 categories: modality, geometry, domain, and approach. The input to the model can be RGB depths and thermal images, or even a combination of them. Also, human pose can be estimated from mocap data. The output can be 2D, 3D, or 4D. 4D means 3D plus time. The pose can be linked to the head, hand, body, or all together. Finally, the most important category is the approach. Data-driven approaches are mainly machine learning approaches that need data to train the model. On the other hand, there are approaches that minimize an objective function such that a blend shape model fits to the observed modality online. Although the blend shape optimization approaches do not require training data, they need a carefully designed objective function. These two approaches can be applied for single versus multi-person problems or supervised versus unsupervised approaches. Okay, in this talk, I try to cover a set of interesting and successful ideas out of thousands of different papers in the literature. I will focus on 2D and 3D body pose plus 3D pose and shape together. Finally, I briefly explain 3D hand pose. I start with 2D human pose regression. 2D human pose regression is the first and simplest approach one can apply. In this approach, the network output is directly X and Y location of the joints in the pixel coordinates. In this case, the loss can be a simple L1 or L2 loss, as you can see here in this image. There are two difficulties for this task. First of all, the manifold of 2D poses is highly nonlinear. Learning proper features to map an image to this manifold will face a lot of local minimum. Secondly, human can appear in any scale and any location on the image. And convolutional networks are not scale and translation invariant. Among many solutions to bypass local minima, there is a simple solution that doesn't require any specific architecture design. In this idea, a bunch of pose regressors are stacked in a cascade, and each stack improves the error of its previous stack. To solve the scale and translation problem, rather than making the network scale and translation invariant, we can apply a pre-processing to crop human bounding box and feed that cropped image to the network. This pre-processing needs a person detector which can propagate its error to the pose regressor. In overall, a better alternative to the pose regressor is to map each image pixel to a probability vector that shows the likelihood of each joint to appear on that pixel. I will explain this idea later on. So the cascade of pose regressors is an iterative error refinement approach. First of all, an initial estimation is applied in the holistic view. This provides a rough location of the joints. Then, in the next stages, a local window centered on the estimated joint is cropped and fed into the network. The goal in this stage is to estimate an offset vector that is added to the initial estimation of the joint location and refine it. It must be noted that the networks in all stages except the first one share the weights. In this image, we can see how iterative the error is refined. The green color is ground truth and the red is the estimation. The error improvement is more visible in the last row here. Although we observe improvements over the stages of error feedback, cascade of pose regressors has some limitations. First of all, it is sensitive to the initial estimations. It means it is quite possible that the local windows do not have any evidence of the joint, for instance due to occlusions or a wrong initial estimation. This can still lead the network towards local minima because of a local evidence and a lack of end-to-end training. Another reason is that the scale of the local window is not optimized per image and per stage. Finally, this solution doesn't implicitly or explicitly learn any structure over the joints in the cascading stages, and the joints can be updated regardless of the others. In this image, we can see some results on LSP dataset. As we can see, the network performs fair but far from to be perfect. For instance, in these examples, left and right legs are overlapped due to the aforementioned limitations. In this image, we observe dense probability maps estimated for some joints by a convolutional network. These probability maps are also called joint heat maps. In this kind of approaches, the last network layer is a tensor with the shape of image width, height, and the number of joints. For single person pose estimation, each heat map can be normalized by a softmax layer. This softmax layer is called a spatial softmax because it is applied on the pixels rather than the classes. Then we can assume the pixel with the maximum probability is where the joint is located. This operator is called argmax. Most of the heat map based approaches are fully convolutional. Fully convolutional means the network doesn't contain fully connected layers. This means a pixel to probability mapping is done through local convolutions, which is an easier problem for the network to learn local joint related features rather than pose regressors. Therefore, it is more robust against subject translation. Heatmap-based approaches are also more flexible in design and still can be combined with pose regressors. Finally, the network learns joint structure implicitly. It is also possible to apply explicit higher-order joint relationships by graphical models, for instance, thanks to the probabilistic nature of the output. An important factor in fully convolutional networks is the receptive field. The receptive field of a network is the area on the image which is used to learn the features for a specific node. The receptive field is increased for the deeper nodes after each pooling. The receptive field and the context are quite important for the joint estimation. For instance, by looking at these images, we are unable to recognize which one belongs to a human or a joint. However, with a larger receptive field, more context is available. We can design networks to have larger receptive fields, for instance by dilation. Or similar to the pose regressors, we can recover from failures by stacking several fully convolutional networks. This also helps to learn more context with respect to the joints. In this regard, a stacked hourglass network is an effective design to solve aforementioned issues. There are three components in this network: hourglass module, intermediate supervision, and sequential stacks of hourglass modules. Now I explain each component. Before that, note that the input image is downsized after a few layers at the beginning. Hourglass module is simply an encoder-decoder with skip connections and a fixed feature size of 256 in all layers and all stacks. A skip connection between corresponding encoder and decoder layers helps the decoder to be aware of local features. This will lead to more fine-grained details in the output. A stacked hourglass network has supervision on all stacks during training. This means a loss is applied on all the stacks. This is called intermediate supervision. The architecture of the intermediate layer is like this. In this layer, a set of 1 by 1 convolutions are applied. By using a one-by-one convolution feature, embedding of each pixel is updated efficiently. Then supervision is applied on this layer. Finally, all the information from the input, output, and heatmap channel are fused and fed to the next stack. In this way, the information is propagated from the beginning stack to the last stack, and the network will converge faster. In this figure, we can see an interesting characteristic of the stack hourglass network. Here, three different networks are compared. The capacity of all networks is equal, but each has a different number of stacks. The x-axis shows each network, and each stack is coded by a different color. The y-axis is PCKH, accuracy metric. PCK is the abbreviation of the percentage of correct key points. In this metric, detected joint is considered correct if the distance between the predicted and the true joint is within a certain threshold. This graph clearly shows that more stacks but in a smaller hourglass module size obtain higher accuracy, for instance here. Although a stacked hourglass network shows promising results, it has some drawbacks. First of all, it is a very heavy network. For instance, the training is not possible for a batch size higher than 15 on a GPU with 12 GB memory. Secondly, joints can be confused with background. And finally, the network doesn't explicitly learn joints relationship in a kinematic structure. It is worth to see some qualitative results of the stacked hourglass network. It is doing a very good job on many challenging images and poses. In the next slides, I will explain how we can update a stacked hourglass network such that the network to be aware of the data structure. First of all, let's take a look at the and/or graph structure. And/or graph is used to solve certain problems where the problem can be decomposed into smaller subproblems. Then we solve these simpler subproblems. And/or graph involve branches where some or all must be satisfied. This figure is an example of the usage of and/or graph for parsing human body. Starting from the root node, human body is decomposed into subparts until reaching to the leaf nodes. As the simplest components of the human body. In this case, the goal is to optimize a model to find the best possible combination of the leaf nodes. An advantage of representing human body in a hierarchy like this is that some articulation constraints are satisfied. Okay, up to now we have a tree structure for part-subpart relationships where the leaf nodes are the body joints. This compositional model has a bottom-up inference. Means we start from the leaf nodes and end at the root. And we can formulate the solution by Gibbs notation for our likelihood maximization problem. In the Gibbs notation, the probability of a solution given an image is equal to the exponential of an energy term normalized by Z. This likelihood maximization is equivalent to this energy minimization. We can formulate the energy term by conditional random field. Okay, but just as a recall, conditional random field has a unary term and a pairwise term. In the unary term, the score over the leaf nodes is summed, and in the pairwise term, the score over the composition of the child nodes are summed towards the root node. Now we want to solve this problem by a deep neural network. So, regardless of the network architecture, we assume unary score phi leaf and pairwise score phi and are given by the network. Also, along with the bottom-up inference, we want to build a top-down inference. I will consider these two items in the next slides, but first we must define an updating rule over these two unary and pairwise terms. So in the bottom-up inference, first we get some scores on the leaf nodes, then the pairwise scores between parent-child nodes are assigned to the edges between them. I call these pairwise scores messages. Finally, the scores on the parent nodes are computed as the maximum negated energy over all the child nodes. This negated energy means the summation of the child score and its message. So now we have a bottom-up inference up to the root node. Now we define a top-down refinement starting from the root. The goal of the top-down refinement is to improve the joint location with respect to the hierarchical constraints. So the output is a refined joint. The joints on the root node don't get updated while the joints on the child nodes are refined down to the leaf nodes. Refinement is done by computing a message from the best parent joint to its children. It is added to its bottom-up score, and the best joint location is extracted over all possible locations. These updating rules contain a sufficient procedure to replicate in a convolutional neural network. Okay, we build our network based on the stack Hourglass network. First, we need to define an AND graph. This is the defined graph with 3 levels, where the level 0 include the leaf nodes. Then we build our network with 5 stacks. The first 3 stacks for the bottom-up inference, 1 per level, and 2 stacks for the top-down refinement. Here there is a tree to compute pairwise messages as shown here. The pairwise score at a given level for a certain node, for instance this one, or this one, is computed as a Gaussian around the line connecting the joints in that level. Although it is possible to increase the number of levels, it has been shown that a 3-level network is a good trade-off between the accuracy and efficiency. This is an interesting image comparing the 8-stack Hourglass results with the 3-level compositional model. These are examples in which the 8-stack Hourglass confuses the background with the joint, in these cases, for instance. The confused joint can be an invalid joint belonging to the background or a valid joint but belonging to a neighbor person. In all of these examples, the compositional model could correctly detect the valid joints. These are some papers for further reading. By reading them, you learn about attention maps, graphical models, and generative adversarial training. Nowadays, 2D pose estimation approaches are very accurate and reliable, ready to be used in real-world applications. In the next slides, I will consider 3D pose estimation. 3D pose is the vector of body joint locations in the 3D space. 3D pose estimation has the same challenges as the 2D pose estimation, plus an additional challenge. In the pinhole cameras, when the world is projected to the camera plane during capturing, the third dimension is lost. Back projecting 2D to 3D is an ill-posed problem because there are infinite 3D joints that can be projected to the same 2D pose. Three-D pose estimation can be categorized in several solutions. A very naive approach is to regress 3D pose directly from RGB image. Another alternative is to estimate volumetric heatmaps and then extract 3D pose from there. It is also possible to estimate 2D pose and regress 3D pose from 2D. Finally, we can estimate 3D pose from multimodal data. For instance, depth image, multi-view cameras, and others. On the one hand, pose regression from RGB image is a difficult task for the network, as we observed in the 2D pose estimation. On the other hand, capturing and annotating multimodal data is not a trivial task, making multitask learning impractical for many applications. In this talk, I will cover these two sets of approaches starting from 3D pose regression from 2D pose. Okay, this approach is also called lifting 2D joints to 3D. Among many proposed approaches, there is a simple but effective approach based on a bunch of multi-layer perceptron layers. The input to the network is a normalized vector of 2D joints, and the output is a normalized vector of 3D joints. We can subtract all the joints from the root joint as the normalization. The input needs an additional scaling normalization. The reason is that there is an ambiguity between subject scale and the distance to the camera. That means when the subject gets closer to the camera, its scale becomes larger on the image plane. Therefore, we need to make the 2D joints scale invariant. The network has two stacks of MLT blocks. Each block contains two fully connected layers with batch normalization and dropout. Then the output of each block is summed with its input. This means the network will learn an offset as the output of each block rather than absolute values. It has been shown before, for instance, in the ResNet architecture, that this kind of skip connection is an effective trick for faster convergence and more accurate results. Due to this design, the input 2D tensor is updated beforehand with an additional column of zeros as the missing depths. This network can be trained with two types of ground truth data. One type is based on pixel coordinate, and the network just estimates the third dimension. Then, given camera matrices, 3D joints can be reconstructed from 2D. The other type is based on the world coordinate, and the network directly estimates 3D reconstructed joints. Okay, in this table, we see the layer parameter sensitivity analysis for the lifting network. In these experiments, 2D joints are detected by a stack hourglass network. The best performing model has an error of more than 67 millimeters. Interestingly, training the network just with dropout has a very high negative impact on the results, while the combination of the batch normalization and dropout performs the best here. Another interesting analysis is when the input and the output do not have the same coordinates in this case. For instance, the input is in pixel coordinates and the output is in camera coordinates. In this case, the network cannot handle the lifting very well. There is a limitation in this kind of approaches. Since image features do not contribute in the lifting, 2D pose error can propagate to 3D and the solutions are suboptimal. Okay, in the previous network, all the joints are connected to all other joints in fully connected layers like this. Given a body kinematic tree, what happens if we group relevant joints in a locally connected layer rather than fully connected layer, like this one? In the next slide, I will consider this idea. Okay, we replace fully connected layers with locally connected layers. And in these locally connected layers, 3 neighbor nodes are grouped. As a result, the error is improved by around 5 millimeters in both pixel coordinate and camera coordinates. It means locally connected layers are more robust against the input to the pose errors. Similar to the 2D pose estimation, we can build solutions based on joint heat maps. A 2D heat map can be extended to a volumetric heat map by adding an extra dimension. Actually, 3D space is discretized into volumes, and the probability of a joint to appear in a volume is defined by a 3D Gaussian, like this one. This is a simple pipeline to estimate a volumetric heat map. The last convolutional layer of the ResNet is reshaped to the shape of the volumetric heat map. In this pipeline, a sigmoid activation is applied rather than a softmax. Therefore, more than one hot area may appear at the inference time. As we observed before in 2D pose estimation, the hottest volume is given by the argmax operator as the joint location. However, there is a drawback in this idea, since the real joint location may appear anywhere inside the volume. This will cause an offset error. Fortunately, this problem can be solved by soft argmax instead of argmax. So instead of sigmoid, a spatial softmax is applied. Then the joint location is extracted by a weighted summation of all volume centers. Another nice property of the soft argmax is that it is a differentiable operator. Up to now, I explained different network designs and data representations, but neural networks are data-hungry models, and the success, robustness, and generalization of a network also depends on the amount and distribution of the data. In this regard, data augmentation is a technique to create new data from available data. For instance, by image flipping, cropping, padding, rotation, color modification, and other things. In this work, a new data augmentation has been introduced. The goal is to corrupt the image by pasting random objects at random scales and random positions. In this case, random objects are fetched from Pascal work dataset, as can be seen here. By doing so, parts of the body are occluded, and the network must learn the correct joint locations. By corrupting the background, the network must learn better fine-grained features of body parts. As a result, this simple approach could outperform previous works without using extra pose datasets in the training. Interestingly, occlusion data augmentation could improve the error more than 15%. Some more reading, including ordinal depth supervision, multi-person spatial temporal, and multi-view pose estimation. Representing human body with joint location has been explored in many papers, but this is a minimal representation of the body. Many information are missing in this representation, like shape of the body, surface, topology, and the gender. It would be interesting if we could estimate these extra data along with the joint locations from RGB images like this. We will explore some ideas in this regard. To do so, first we need a rich representation of the body. In the domain of 3D object reconstruction, there are several non-parametric representations, like the surface point cloud or object volume voxelization. These representations are okay for real-world free-form 3D objects, but still not rich enough. In 2015, a parametric generative body model has been introduced, so-called SMPL. In the recent years, researchers started to build their deep models vastly based on SMPL model. SMPL is a statistical parametric function which maps shape parameters beta and pose parameters theta into a 3D mesh. SMPL has a template average body mesh with a set of rigged joints. Given shape parameters, an offset vector is computed for each body vertex, which is used to update the template mesh. Template joints are also updated by a regressor. The template is updated once more with a small pose-based displacements due to body soft tissue behavior, and these new offsets have a small contribution in the shape deformation. Pose parameters are relative rotation matrices in a kinematic tree, which are computed for each joint with respect to its parent. Finally, the updated template mesh, this one, is posed by rotating body parts relatively in a kinematic tree. SMPL model has several characteristics. First, it is differentiable, which yields the possibility to be used along with deep networks. Secondly, it doesn't constrain invalid pose and shape values, which makes some difficulties to the network. Finally, SMPL is a generative model which allows us to generate mocap data for free. SMPL is a parametric model. Therefore, we can regress its parameters directly from an image. As we observed before, this is a challenging task for the network. Besides, SMPL is sensitive to the noise and it may generate artifacts. We first start by checking this idea. Annotating an image with SMPL parameters is not a trivial task, especially for real-world images. Although some semi-automatic annotation pipelines have been proposed by researchers, it is likely to be able to estimate pose and shape without 3D supervision. In the first step, we consider supervision just by 2D joints. In this pipeline, an encoder is used to regress pose, shape, and camera parameters. Then 3D joints are reconstructed by SMPL and projected to the image plane by camera parameters. Finally, an L2 loss is applied between ground truth 2D joints and projected SMPL joints. Okay, let's see some results. Although 2D joints match with ground truth in these images, the reconstructed bodies are some monsters. The reason is that there is no constraint on the pose and shape parameters. The solution is to regularize the space of the pose and shape parameters with real humans. These days, there are many mocap and scan datasets of human bodies. We can use them to learn real distribution of human body. This can be done simply by a Gaussian mixer model or alternatively by adversarial training, as has been done here. In the adversarial training, a discriminator network regularizes the estimated pose and shape parameters by checking if they lay in the space of real humans or not. This pipeline can be updated with an iterative error feedback, and in the case of available ground truth pose and shape data, it can be trained with 3D supervision as well. In this table, we can see how accurate this pipeline is comparing with other approaches. There are two common metrics in 3D pose estimation: mean per joint position error and reconstruction error. Reconstruction error is the per joint error after rigid alignment of the prediction with ground truth via procrustes analysis. As expected, a supervised approach is more accurate than unsupervised. However, unsupervised approach is more applicable in the real-world applications where 3D data annotation is not trivial. Also, comparing to the methods that just predict 3D joints, which are these ones, we can see that pose and shape regression is far from to be perfect. An alternative approach is to predict body vertices as the network output rather than SMPL parameters like these ones. Two types of these approaches in the literature are based on graph convolutional networks. which outputs a complete body mesh, or a volumetric stacked hourglass, which outputs a set of sparse surface landmarks. These predictions are not parametric, but can be easily mapped to the SMPL parameters to form a parametric solution. This is possible with any MLP-based encoder. Next, I explain the solution based on the graph convolutional networks. First, let's briefly review graph convolutional network. Image-based convolutional networks are specific forms of graph convolutional networks where the graph is defined as a grid among image pixels. In the graph, each node may have a different degree. Features are assigned to the nodes and weights are assigned to the edges. Graph topology or adjacency pattern is shown by a Laplacian matrix. Multiplication of the Laplacian matrix with the normalized diagonal matrix of node degrees will give us a symmetrically normalized adjacency matrix. This matrix defines how filters are convolved to the features. In this basic formulation, the weights are not shared among all the nodes, like this. To be able to apply graph convolution on any graph with any topology, weights are shared among adjacent nodes. Also, convolutions can be applied on arbitrary levels of adjacency, and batch normalization, Dirac, and other tricks are applicable. Finally, due to the weight sharing, graph convolutional networks require more filters than convolutional networks. With this explanation, now we can build our graph CNN mesh regression. The idea is simple. Vertex coordinates of a template mesh, like this, are updated through graph CNN by the aim of image features. More specifically, extracted image features are copied to the template mesh nodes along with vertex coordinates. And after a bunch of graph convolutional layers, per vertex coordinates are regressed. The network can be trained by any loss like L1 or L2 loss. Now we can regress SMPL pose and shape parameters. Via MLP network from a dense mesh. Like this one. A dense mesh. Like this one. Okay, graph convolution lens features based on local surface patterns. This is an interesting image. In this regard, an interesting image. Replacing graph convolution with fully connected layers. Local minima. Cannot deal with local minima. Like these images. Also, quantitative results in this table illustrate that mesh regression is more accurate than SMPL parameter regression, comparing these with this. A limitation with graph-based mesh regression is that it overfits on the training set and requires additional data during training. Okay, an alternative approach to the dense mesh regression is the sparse landmark regression. Landmarks are single points on the body surface. Annotating the landmarks is an easier task than a dense mesh. All the points on the body surface do not have the same importance, and some are more representative of the surface geometry. Some studies show that 70 landmarks are sufficient to represent the whole body. The number and location of the landmarks can be optimized for specific applications. In this work, 18 landmarks has been used, as shown by red dots. We observed before the success of stacked hourglass network and volumetric heat maps. Landmarks can be estimated by a volumetric heat map along with the joints as the output of the stacked hourglass network. The output layer of a stacked hourglass network can be updated to form a volumetric tensor for this task. I must note that this is a very heavy model and consumes a lot of memory during training. Also similar to the compositional models, volumetric heat maps may not be limited to the joints and landmarks, and pairwise heat maps like these ones can be added to the output. In this case, 4 limbs for the legs and arms. Now we can regress SMPL parameters from joints and landmarks. Here, instead of directly inputting the estimated joints and landmarks to a MLP network, they are factorized into 2 feature vectors. One to regress shape parameters and the other for pose regression. Here the assumption is that shape and shape parameters are independent to the pose. Shape features B are relative joint lengths with respect to the kinematic tree, and pose feature N are relative joint norms with respect to the kinematic tree. In this network, gender is also regressed along with the shape parameters. These are some example ablative results. Training SMPL regression without landmarks converges to an average shape. Landmarks not only improve the shape estimation, but also disambiguate joints orientations. These are some samples. It is also worth explaining the training procedure. Training the whole model end-to-end converges slowly. Therefore, stacked hourglass and SMPL regression are trained individually at first. Then, for end-to-end training, the SMPL regressor parameters are freezed, and just stacked hourglass is fine-tuned. This procedure further improves stacked hourglass results, as can be seen here. This is the results before end-to-end training, and these are the results after end-to-end training. Also regarding this image, SMPL regression has a small generalization error, mainly due to the gender failures or global orientation. Procrustes alignment of SMPL output with stacked hourglass output improves this kind of failures, like these ones as the gender or these ones as the pose failures. It is also interesting to compare the results of this approach with 2 previous works I explained, that is Kanazawa and Kolotorus. This approach works best among the competitors, as can be seen here, for mean per joint error. Also, it is interesting as well that training the stacked hourglass end-to-end moves it to the top of the list comparing to the state-of-the-art results for 3D joint estimation. Okay, up to now we explored body pose estimation approaches in RGB images. It is worth to take a look at the other modalities and target domains. 3D hand pose estimation in depth images has been an active topic in the past decade. Advances in capturing devices like Microsoft Kinect makes it possible to build commercial applications like these ones. The challenges in the hand pose estimation are mainly because of the small size of the hand while it is moving fast and can be easily occluded. Hand pose can be used in human-computer interaction, virtual reality, training robot hand, and gesture recognition, among many applications. All the approaches we considered up to now were based on 2D CNNs in this row, a mapping from pixels to coordinates or to volumetric heat maps. However, in depth images, pixels can be converted to the volumetric representations like these ones. And thus, 3D CNNs are applicable. In this regard, we consider an approach called voxel to voxel mapping. This is the architecture including residual and hourglass blocks. All these building blocks are based on 3D CNNs. And despite of the accurate estimations of this approach, it is a heavy model in both training and testing. Also, it's a unique architecture not useful for transfer learning. That means fine-tuning from pre-trained models on big datasets is not a possibility. These are some example results. These are the results based on an ensembling over the last 10 trained models. It means the models of the last 10 epochs are saved. Then at the test time, depth image is inputted to these 10 models and the results are averaged. Although this approach gained more than 20% improvement over a single model, it is not practical for real applications. These are some more readings, including pose-guided region ensembling, global local pose, feature mapping, and RGB-based pose estimation. In conclusion, human pose estimation is an active and important domain in computer vision field. Heatmap-based and compositional approaches show state-of-the-art results. Finally, richer body representations than just 3D joints are more interesting. Currently, full body reconstruction, including texture and garments, is becoming an active topic. Okay, I'm done with the presentation. Time to questions.
All right, now we'll have the Q&A part. Salam Meysam, welcome and thank you for your interesting survey on this topic. Are you with us?
Hello, yes, I'm here. Do you hear me?
Yeah.
Okay, any question can be asked in the chat or directly from me. So
all right. Yep. Okay, I think we have one question about the applications of the pose estimation, which was already asked. And if anyone has any question, can type it in the comment section.
yeah, okay. Regarding the applications, I think everything regarding the humans can be the pose estimation can be used in applications regarding the humans. For instance, the online purchasing. For instance, when you want to find the right size of the clothes. Another one is a sports analysis, when you want exact movements of the joints of a player. In movies, for instance, the 3D pose and shape estimation can be used for editing, for instance. If you saw some applications of animation generation by using the mocap data, so the mocap data can be converted to a full mesh of the body, and then you can do many things on top of that. Other applications can be human-computer interaction. For instance, in the case of hand pose estimation, you can interact with the computer with your hands. So this is called gesture recognition or activity estimation. So other applications I can mention in the health care for detecting anomalies on the body. I don't know, in the gaming and virtual reality. Also, I mentioned at the end of the presentation about the garment estimation in 3D. So this is the future. So now we have just the pose in 3D joints, then estimation of a naked body surface, and then we want a full reconstruction of the body. There are many applications in this domain. So let's see what other questions we have. I see many.
Could you please introduce several free and public data sets for pose estimation?
Yes, for 2D pose estimation, we have LSP, MPII. For 3D joint estimation, we have Human 3.6 million dataset. For hand pose, we have NYU, MSRA, and hand 17. There are some other datasets which are old and not used. I mean, the pose estimation is solved on those datasets, like Human EVA, which is very old. There are some other datasets. At the moment, I don't remember the names, but there are some newer datasets on this topic.
All right. Is there any real-time pose and or shape estimation, state of the art?
Yes, the networks that are using ResNet 50, they are more or less real time. The one that I introduced as unsupervised pose and shape estimation, it is using ResNet and it's real time. But sometimes you need pre-processing. For instance, if it's a single pose estimation, I mean, you have a single person on the image and you want just to estimate the pose of that single person, then you need cropping the person bounding box. This cropping needs some pre-processing, like detecting the human bounding box first, and then another thing here is maybe if it's a video-based application, maybe you want to have camera parameters calibrated by SLAM approaches. I don't know, but just estimating the pose can be real time. Yes.
All right. How do you deal with missing data in videos?
Missing data, we can have many definitions of missing data. In what kind? Missing data as the joints in training, or missing data, I mean, for instance, just upper part of the body, or missing pose locations on the image.
Aryan, you can elaborate on this question more in the comment section. Well, if I think I've already seen some applications where just half of the body is present in the picture, and he might want to know about this kind of scenario.
Yeah, we can discuss both. I mean, the missing data on the image and missing data on the ground truth data. So, all the applications that I presented, they need a full body to be presented on the image. There are other approaches, but you can kind of help the network by data augmentation a little bit. For approaches that just use on the part of the body, you can move from holistic view to the local view. So what you can do is that you just detect the joints separately from the others, and then you stack all the joints together, and then the missing ones can be estimated on from other applications. Another thing here is that mainly this is useful in multiple pose estimations. So you can get some results from the context of the image. So by interacting between people. So when people are interacting, you may find some missing joints by estimating the interaction, and then the motion of the joints can show us how exactly we can find the future joints. Regarding the missing joints in the ground truth, you can use denoising autoencoder, for instance, to find the missing joints. So you first detect the available joints, and then the missing ones can be estimated from available ones. Actually, in the last presentation of 3D pose and shape estimation that I introduced, there is a denoising autoencoder that can deal with that, but I didn't show that, but it's available. So you can benefit from these. Also, you can add SMPL on top of this and improve more the results by let's say some regularization on the joints. I can send later maybe some references regarding this.
All right, thank you. Can we use motion estimation techniques for pose estimation? For example, optical flow?
Yeah, you can use any modality that you want. If it's in a video, then you can use optical flow, but optical flow is a little bit time consuming. So depend on the application, you can use it or not use it. But recent approaches mainly do not use optical flow. But yes, you can use any modality you want.
All right. Is the hand recognition so simple that we can run it on a cell phone for real-time purposes?
I guess so. Because recent approaches using transfer learning and ResNet, I observed very accurate applications of the hand pose estimation. So yes, it can be done real time. Also, you can find some videos on the internet that the person can interact with the computer in real time. It's not on mobile phone, but I guess it's possible.
All right. Is it possible to use these approaches for animal pose estimation too?
Yes. There are some papers regarding this. It's not based on human models, but you can have animal models. And as soon as you have animal models, you can use these models, these balance shape models, to detect the surface of the animal body. Or if you have ground truth data, yes, everything is possible. Yeah.
Right. Can we use pose estimation networks as a pre-trained network to action recognition task? Is it effective for action recognition?
By sure, we can use pose estimation for action recognition. And I remember in the past, because I do not know much about action recognition state of the art, but few years ago, I saw some papers using pose for action recognition as an extra information. But just action recognition from the pose, I don't know how accurate it could be. It quite depends on the accuracy of the detected pose. Also, in the action recognition, you should take care of the windows that you select. So, but I think it's quite useful to use in the action recognition. Actually, at least for the hand pose, I know it's kind of possible.
All right. Okay. Seems like we don't have any more questions. All right. So I think we can conclude the session here. Any last words?
If you are interested in this domain, the future will be full body reconstruction. Now we have very good data sets on 3D pose. As I mentioned, 2D pose estimation is already near solved. For 3D pose, just 3D joints, it is also, the approaches are quite accurate, both in laboratory data and also in the wild data. Now, the applications for the full body reconstruction, not just a naked body, also the garment. The model that I showed, the SMPL, is rigid. so it doesn't have soft tissue information of the body surface when the person is moving in an action. There is no soft tissue. Everything is fixed and rigid. So if you are interested, you also can work on that. Also, if you are interested, we have a challenge regarding the garment reconstruction at New Ribs, and it's quite interesting. So if you are interested in this domain, you can register and download the data and see how you can deal with this problem. And we will be happy if we see you there.
All right. Thank you, Meysam. So this concludes this session. Thanks, everyone. Enjoy the next sessions afternoon. Goodbye.
Goodbye.